Hello again, folks. Today we're going to be starting with a new chapter, chapter 6. And if you look at the calendar, we are now in November. Right? We should be covering section 6.1 to 6.4. Realistically, what that means is that I'm going to give you homework in just 6.1 and 6.3, but I want to cover the material, at least so that you see it, from 6.2 and 6.4. It's basically transformations that are applying to this stuff. Okay, I'm going to give you the models and what the effects would be. But let's get started. All right. Now, from 6.1 to start with, I'll have it erased nicely. Here's an overview, as always, to get us situated. Okay. Need some more. In the subject of functions, you're well aware at this point there are basically two types. There are the algebraic functions, which we have been talking about, and then there's this newfangled thing, which are known as the transcendental functions. That's really where we're starting today, right, with the transcendental functions. You can basically say to yourself, okay, these are non-algebraic somehow. Okay. What that means is, well, there's subcategories here, if you will. In chapter 6, the two that get discussed are the exponential and their inverse, which is the logarithmic. Then later on, I want to say it starts in chapter 7, at least, is the trig functions, which we will get to eventually. Okay. It's funny that they called non-algebraic transcendental. Transcendental is they're above this somehow. They still incorporate everything that we're familiar with. Basically, what is exponential is section 6.2, pardon me, 6.1 and 6.2. And what is logarithmic is section 6.3 and 6.4. And this is together chapter 6. Now, most importantly, understand that these two things are inverses. So if they're written in the style of a function, sure, there would be f of x and the other would be f of x, but let's start with something a little bit more basic. Sorry, my throat is closing. I think I'm allergic to my mouthwash. If you had this written in more or less the usual way, which is y something, let's go with this. How is it distinct from an algebraic function? Normally the algebraic functions have the variable x as either a numerator or a denominator. Right? If it's exponential, what is interesting about it is that the input variable x is an exponent itself. Right, so you'll see that it'll be slightly smaller font raised up higher. Being that these two things are inverses of one another, remember that the inverses are basically the x and the y value swapped. All right? You really should resolve this to solve for x, right? But eventually what you're going to get, since it's not too complicated, is this instead. Y is equal to base y up here instead. X. Yeah, maybe I should have done that to begin with. Y said it's solved for y, x is the exponent, it's solved for x, y becomes the exponent. Right? They are inverses of one another, right? Which has implications for their drawings as well. All right. Before we get to that, let me just give you kind of an what do you call it? A sneak preview, if you will. Even in spite of this being the arrangement, since they are inverses, oftentimes what happens is that this gets rearranged to solve for y, all right? And it ends up looking like this instead, all right? Y equals the log of base b of the argument x. It is still preferred, even though this is exactly what this logarithmic function would look like if you just use letters x and y. It is still preferred to have something arranged as though it were y equals, right? And so they will throw this symbol log in, or this sequence of letters log, all right, to represent that this is really what it originates from, all right? Notice that there's a base here, subscript in this case. This is regular font size, but the bases are the same base, right? This is rearranging x equals b to the y so that x is still the input value of a function, okay? And then, to go one step further, they will resort back to function notation. So in this case, you'd see the following. B to the x instead of y. All right? I personally like y, but hey, we're calling this a function, so why not? All right. You could do the same thing here. I'm just, for lack of board space, going to write it above y. Okay. Now as for the graphs, you have, and I'll mention the packet today. This packet of information will be available to you. I have to make a new page in Canvas that is specifically for Chapter 6, but it is Old Faithful, right? Our parent toolkit function page, right? You've seen this at least twice from Chapter either 2 or 3, and then most recently again. We have covered basically these 7, right? What we're going to get into now are exponential graphs, functions, and although this is a specific type, this is the natural log, we'll get into that later. These are what the graphs would look like in general. And notice they have the domains written and the ranges written in interval notation, right? So still very useful, right? What's interesting about exponential functions is that, like rational or reciprocal function in this case, there's an asymptote. It doesn't have 2 of them, it only has 1 of them, all right? And its inverse has an asymptote in the opposite orientation. So if this is a horizontal asymptote, this has a vertical asymptote. Okay? Here's a quick picture again. Let me get rid of this. I'll draw what the graphs would look like, just to express this relationship a little bit more clearly, or remind you. The important point to sort of remember, as in many of these other cases, not entirely, reciprocal is one exception, they go through the origin, all right, and they include the point 1, 1 in these cases, all right, and in some cases negative 1, negative 1. When it comes to the exponential function, the key point that you should always bear in mind is 0, 1. That would help you, at least if you were drawing it by hand. This is a y-intercept truly, but it's 0 for the x value, and then it's 1 for the y value. And your graph would look something like this. Arrow this way, arrow that way. All right. Now, that's exponential. Right? Being that the logarithmic function is an inverse, insofar as the graph is concerned, remember that inverses, the x and the y values are swapped. So if we could figure out a swap of these two figures, a 0 and 1, put a 1 in the place of the x and put a 0 in place of the y, that would be here instead. 1 comma 0. This is what the log function would look like. Just to get it out of the way. And I'll put this back over here. That's what the inverse would produce. This is log. Okay. Remember how you could tell, aside from analyzing the ordered pair coordinates, if two functions are truly inverses, they would have sort of a dashed line. They would be as if they were reflected not through a horizontal or diagonal line, but through a diagonal line that goes right through the origin. And I'm just going to put this as dashed because it's not really supposed to be there. It's more or less like an imaginary mirror or hinge, you know. Y equals x. These are truly inverses because they seem reflected over the diagonal line y equals x, right through the origin. Okay? Basically, that's as much of the graph as I would memorize by heart, all right? 0, 1, all right? And that it's a curve rather than a straight line, all right? And 1, 0 for log, all right? Everything else will just be some kind of a transformation. It might get squashed slightly, it might be up a little bit higher, all right? But you start with these key points, right? In the same way that you would want to remember certain key points from these more basic graphs, like the origin 0, 0, and 1, 1, and negative 1, negative 1. Or 0, 0, 1, 1, negative 1, 1, and so forth. Right? The most basic 2 or 3 points will get you pretty far, right? Insofar as graphing, if you were going to do it by hand, you know. Okay. So let's talk about this more in depthly now. To prove that this forms a curve and to illustrate why it is different from some other type of function that may be linear, let's generate some points. I washed my eraser, so it's a little bit more cooperative today. And still doesn't do it really easily. If you print out from the packet this next page, we want to brute force generate some dots. Right. So I modified my test point grid so that it looks a little bit like this, and I made extra spaces in this case. Right. I'm not using intervals, it's not really important right now. I'm going to give you some inputs that I'd like you to write it here and then do the calculation yourself, or just watch me. All right, we'll generate some y's and then just put them together so that we have some points. And then I'll graph it. Hopefully this is nice and clean. I'm going to wipe down. All right, humor me, I have to unfortunately draw this from scratch. I don't have a projector. Okay. Probably should have done that first. I wish I had 3 hands. Okay. Is our x input. We'll do a calculation when x is the input. That will give us a y. All right. I'll write that as the answer here, and then we'll put them together as an ordered pair. Let us try the most basic function. Y equals 2 to the x. All right, we'll substitute some values in place of x here, calculate what they ought to be, that will figure out a y, we'll pair them together again. Okay. So let us say that we use small numbers. If you're doing this brute force, remember brute force works for everything, right? Small numbers would be to your advantage, right? Because then you don't have to suffer. If I inserted -3 here, right, in place of x, do remember that when you have a negative exponent, the effect realistically is to shift the location of this base to a denominator. All right? And I'm kind of skipping steps here, but it would end up being this instead. Right? What they would tell you in a textbook is probably this. They'd say, well, the negative just simply means write a reciprocal of this, and then you could just leave the 3 exactly where it was. Right? But then you would have to distribute the 3 anyhow, both to the top and to the bottom. In the case of the top being that it is 1, it's always going to be 1 no matter what. So this is me skipping steps. 2 to the third, on the other hand, would be what? 8. Right? Which means that this would be your y value, strangely, the fraction 1/8. And if you paired them together, you'd have x comma 1, pardon me, -3 comma 1/8. Right, already we have one dot. And we could graph that in a moment. If you did another one, I'll do this a little bit faster. -2. We would insert -2 in place of the x value up here, just as I had done it there. Okay. Once again, the effect being that there's a negative is that this is now a denominator. Skipping steps. All right. And you would end up with 1/4, which means that this would be -2 and 1/4. -1 substituted in place of x would give you 1/2, which is just reasonably 1/2. And you'd have this. I'll do 2 more. Well, at least 0, 1, and 2. All right. See if I can fit this. Y equals 2 to the 0 substituted. Virtually everything, with the exception of 0 as the base itself, would be equal to what? 1. Right? This comes from the quotient rule, basically. So this is just 1. All right. That means, notice this point, 0, 1. Familiar, right? He's becoming familiar. Then you have y equals 2 to the first, would be 2, and you would have 1 comma 2. And just to do another one, y equals 2 squared is 4, so you'd have this point, 2 comma 4. That's a little sloppy. All right. Now, if I were to graph this, and I'll try not to do it out of control here. I'll graph these points, plot these points. Probably don't need as big a board as this, but that's what we would be working with. Right? At -3, 1, 2, 3, I would just barely go above the x-axis because it's 1/8, it's not even a half. So there would technically be a dot very close to the axis there. If I did -2, -1, -2. 1/4 would be slightly higher than that. Slightly higher would be about there. At -1 would be here, and 1/2 would be right smack in the middle. And then at the origin, 0, 0, I would go up 1, and I'd have a dot here again, which is, again, that point that's particularly useful. The y-intercepts, technically. Then if I did these, which are slightly obscured here, 1, 2, over 1, move my thing slightly, over 1, up 2, you see that it sharply curves now. It's a little bit more obvious. If I went to 2, right, it would be up to 4. 1, 2, 3, 4. Right? And I didn't do 3, but if I put 2 to the third, it would be 8. So here's 3 here would be 8. 1, 2, 3, 4, 5, 6, 7, 8. And you can see, even using this most basic exponential function, where it's just a 2 here, right? And the x variable here, no extra features in front or behind it, that it makes this distinct shape. This sharp curve, it's a curve, I shouldn't say sharp, it's a curve. Right? Curves up. Right. This is a different situation to something that would be linear. Right? Distinctly different. If you had a function that was, as you know, purely linear, and the most basic type would be the identity function, y equals x, no extra features here, nothing behind it, nothing of a higher degree other than 1, right? It would be perfectly 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, and backwards, 0, 0, negative, negative, -2, -2, -3. And you'd have a line that is a perfectly diagonal line. This would be like 45 degrees if you wanted to measure it. There's quite a distinction here, right? This is something that exhibits an exponential growth versus something that would be a linear growth or a linear relationship. Okay, and it has a lot of applications. I actually have a big diagram to draw you later of different applications for this. Okay. All right. Let me get rid of this for a moment. Change my mouthwash. I think it might be killing me. I think it's funny. I wouldn't expect to be allergic to something like that, but I think I am. Slow, really effective. I need a sip of coffee to keep me awake. I have to constantly switch between one and another. Okay. All right. Now, what we're going to come back to eventually later, towards the end of the chat, I believe it's like section 6, 7, or mathematical models, but I'll give you, again, as something of a sneak preview. Math models are basically equations, functions, right, that we use for practical purposes. All right, so again, we're discussing exponential growth. This has applications in science. also in statistics. And then there is also exponential decay. Which is just the opposite. Now, here again is a general sort of function, f of x, and we'll have a base, whatever it is, and there'll be an exponent that is the actual input variable in both cases. What would cause something to be an exponential decay is to insert a negative in front of that. And then you'll see a graph that looks just like the mirror image, basically. Now, it is possible also that there could be a coefficient up in the front. Right? That's not going to affect whether it's growth or decay per se, but it is feasible. It wouldn't be immediately affected by the exponent. Right? It's not like they were grouped together in parentheses. It's just a coefficient adjacent. Right? When you have a situation like this, the a value becomes the initial value. You might say starting value. And then the point that would have been 0, 1, right, would instead be 0a. Right? That's the y-intercept. B is referred to as the growth factor. Okay. In the last problem, the most basic example of an exponential function, I had put the base of 2. Right? The base can't be 1, right? Because if it were 1, right, no matter what you would use for the x input, it wouldn't be a diagonal line even, it wouldn't be a curve certainly, it would just be a horizontal line. It would just be 1, y equals 1. So b has to be greater than 1 in order to cut the mustard here. It can be something, let me adjust this. It can be something greater than 0 in general, but it can't be equal to 1. Okay. Just to be perfectly precise. Okay. Now, insofar as the graphs are concerned, the last example looked something like this. There was a point, again, I'm going to generalize even further than 0, 1. I'm just going to call this 0a. In the last instance, technically the a value would have been 1. And the curve looked like this. If you have a decay instead, it'll go through the same point, 0a, but it won't be oriented curving up. Instead, what you'll get is a curve down. Okay, that is primarily for this reason, that there's a negative attached to the exponent. I feel like my thing is sideways. That doesn't help. Okay. Leave it alone. There. Zero A. Okay. Notice, right, it's not really super important right now, but this has a horizontal asymptote. That's the y equals 0, or the x-axis. Right. And this similarly has that same asymptote. It will approach that, but it will never reach it. word problem. If you look again in the packet of materials, right, I have this word problem to sort of get your feet wet. Right. So do print this out and we'll do the work here if you like. All right, in 2006, 80 deer were introduced into a wildlife refuge. By 2012, the population had grown exponentially. So if you had to write an equation from scratch, you have a skeleton to choose from, this one or this one. If it just says exponentially, one could assume it's growth. Right? Well, maybe you shouldn't assume, but it's going to be growth in this case. Right? Really, if I analyze these numbers, it goes from 80 deer to 180 deer. Right? Okay. Using this information and the appropriate model, the function of x is equal to a b to the x. Write a function, just label it as n, the function of t, where n is the population as a number of deer, and t is time. Okay, so the number of deer would be a function of time. We're going to use what's written in purple here as a model. Now I'll erase this because I just need the space. So if we take this skeleton to work our word problem about deer population, f of x is equal to a b to the x. Right. We would need just to pluck out the information from the paragraph. All right, to fill in for the value here, A and B here. Okay. All right, let's start with that. All right. What is A? A is, again, the starting value. All right. And they often in textbooks will use this phrase instead, the initial value, but it's basically the starting point. All right. In the data. Right? If you analyze this, and I purposely put it in color, which of these two numbers, 80 or 180, is the starting number of deer, technically? In 2006, 80 were released into a wildlife refuge. 80 is the starting number. So if 80 is A, that would fit here in the model. Now the next thing is to figure out the B value. What is B? Right? That's a little bit more tricky. Right? That is the growth factor. It's the base, basically. Right? We know that it can't be 1, and it's just something that's positive primarily. Right? But what we can do is substitute some given values here. It might be a little bit easier to finagle if I just change this to temporarily y equals 80 b to the x. Right. Notice that I have 3 variables in this scenario. I have y, I have b, and I have x. I'm really looking for b. So algebraically speaking, right, if I'm going to solve this, I need to know what this is, and I need to know what this is, and then I can isolate it to solve for b. Right? You can glean that information. What is a y value? What is an appropriate x value? All right, from the rest of the paragraph. There is some little tweaks here and there. Like for instance, instead of f of x, they're asking you to call it n of t, and if t is the variable, the input variable, then it would be here in place of x. And it would be here in place of x as well. Right. and this is really an n then. Still three variables, n, b, and t, but we need to know what the n number of dia is after a certain amount of time, and we need to know how much time has transpired. Okay, so if you look again at this, right, some of it is obvious and some of it is obscure, right? This data, for lack of a better phrase, stretches from 2006 to 2012. That's the span of time. How many years is that? That would be a span of 6 years. So you have a 6 in place of that variable for t. All right. The number of dia after 6 years, all right, is how many dia? 180. Okay. By 2012, the population had grown exponentially to 180 dia. So you would insert a 180 here. All right. That means that you have this equation. To make it a little bit more clean, right? And it's sufficient insofar as looking for b, right? So rearrange what you can algebraically. I'll erase this because I kind of need the space. And then I'll work over here. I have 180 is equal to 80 times b to the 6, right? And I'm trying to isolate b to solve for b to figure out what it is. I would divide by 80, that coefficient, both sides. Right? Pull some tricks. If you're not using a calculator, pair of zeros goes away. I would really prefer for this to be a whole number naturally, but if you divide 18 by 8, you know that you would get a decimal. Right? Rather than use a decimal, let's use the improper fraction. So if this is 18 over 8 and we divide it by the GCF of 2, then this would reduce to 9 over 4. Right? It's improper, but it's still simplified. On this side, we have b to the 6. Right? Remember from, I think it was chapter 2, right? How would we get this to just be b rather than b to the 6th power? B to the 6th, yeah. You could do it one of two ways. You could write it in radical notation, or you could write it in rational notation, but you would need to perform the opposite operation, right, to cancel. So the easiest thing, and you would have done this in chapter 2, is raise this to a reciprocal here, right, for the sake of cancellation, and then if you've done it to this side, you're obligated to do it to the opposite side. So you'd have 1/6 here. What happens is that when you multiply, or when you raise an exponent to an exponent, even if it's a fraction, you multiply them, and that's like multiplying a number times its reciprocal, which cancels it to 1, right? Which frees it up to just be what we were after, which is b, right? Now, insofar as this number is concerned, you could figure out that this would be 1/6 applied to 9 and also to 4, right? But it's never going to be a nice number, right? So what we'll do is we'll plug this into our calculator now and get an approximate. In this case, you're going to have no choice. You're going to have a crummy decimal because it's irrational. Right, so a couple of things you can do. Right, start with a blank screen. If you want to enter something like this, right, use parentheses. Right, you could just use n/d. I'm a little bit particular about this. I like to use things in the intuitive fraction style of writing, so n over d, which you can get to by pressing alpha and then F1. Enter. And you see it has it in the intuitive writing here. One thing stacked on another. 9/4, close the parentheses, and it looks like that. Then use the caret symbol, and you get it into an exponent. You could do the same thing if you want to. This is being really geeky. And it will look like that. Just put 1/6 either way. 1/6, right? And now you see that you have this terrible decimal, 1.14471, whatever it is. Okay, let's round it to, let's just say, the 10,000ths place. Okay, so where the 7 is. Based upon a 1 here, it would just be about 7. Okay. That means that this b value is about equal to 1.1447. Okay. And having gotten that, we could now fill out the skeleton a little bit better. Okay. This is what we have to generalize. X. These are the conditions that the question required, that we call it number of dia as a function of time, and of t then. The a value we figured out was 80. And the b value is this. $1.1447. To the x. Okay. If you wanted the more precise incarnation of this, it would be using this expression, all right, tucked into where it's written in blue. You'd still have to have the x here. In which case it would be, whatever it is, x/6, so such and such. Okay. Now, they didn't ask you to do this. No. Actually, one thing I should do is change the variable. If it's a function of t, instead of x, I really should use a t here. So that is your input. Alright, I think I have a limited space here. So I need to clean up a little bit better than I have. And throw this out. Be right back. What I would do is, let's just see how this would draw. We'd have to finagle it, unfortunately, because of the limitations of our calculator, believe it or not. We could enter this into our calculator to draw it. We would just simply call this y and this x again. All right. But if you do that, all right, let's say that you go into here, y equals, and clear out what's there. All right, and then enter this, all right, at least this half of it, 80 times that. All right. I'm going to use parentheses. Again, you could, if you wanted to be very precise, input this in place of there. I'm just going to use the decimal we have, 1.1447, and then raise up an exponent of x. So you have something that looks like this. Now remember, as always, you may have to adjust the dimensions of the screen. but we'll see what happens first, right? So I'm gonna hit the automatic here, zoom, Z standard, 6. Let's see how nice it is. If after this is supposed to be like the little clock here, hourglass. If you don't see anything, it means that the scale is off. So don't be intimidated. What you could do is zoom fit instead. All right. Zoom fit is lower in this list, kind of in between. Go to zoom fit and it will adjust it automatically. And it'll be perfect, but it will be usable. Those are all 4 quadrants. Notice that it's just the upper 2 quadrants at this point. And then you have a curve. Notice that it is an exponential curve. Okay. Right, now, if you hit trace, right, it hits automatically where x is 0, and there's your intercept. Remember, this is A. Right? And the y-intercept is at 0, whatever A is. So normally A, at least like in the very first example, it's just 1. That's why it's 0, 1 is important. But this would be 0, 80 in this case. And you could use it to make predictions about the number of deer after X amount of time, or T amount of time, whichever you prefer. So according to this model, all right, how many deer should there be in 1 year? 91 point something, 576. Right? And there's no such thing as a half a deer, right? That's terrible. 91, almost 92, right? After 5 years, all right, 157, right, 0.2. So 157 deer, all right? The scale, all right, once you get past 6, it might give you an error message. That just means that you got to back off in terms of your view, right? But let's see, what is it for 6? It should be 180, all right? It's close to it because of the decimal that I used, 1.79998. All right. Try 7. That's okay, 206. Eventually we'll get off the screen. If I did 10, it's just barely fitting. Here's 10, all right? Try 11. Then you get an error message. The only reason I'm mentioning this is I don't want you to think that you did something wrong when you get an error message. It just means that the screen dimensions have to be adjusted. Why it doesn't just automatically correct itself, I don't know, but hey, I didn't program the calculator. All right, x equals 10 is just barely fitting in this window. And it gives us an approximate, 309 deer. If you did one number higher, 1 year more, you see that you have, it would be off the scale in terms of the x dimension, t. All right, and it gives you an error message. How do you get around that? Well, let me go to it. I'll just zoom out slightly. So go to 3. No, sorry. Zoom, you gotta hit enter. 3. Enter. You're just a little bit further away. There's the drawing. An exponential curve, right? Now when you hit trace and you hit 11, it's still within the frame of the window. So 1, 1, enter. And there's no error message, right? There shouldn't be an error message to begin with, but hey, that's the way it is. All right, it's not your fault though, so don't reproach yourself. All right, turn that off now. Okay. Let us move on here. All right. Let me see if this will erase now. Okay. All right. Let us say that you had to write a function given 2 points rather than a starting value. Points. Right. Okay. Let us say that you had to find the exponential function given these 2 points, -2, 6, and let's see, 2, 1. Okay. Start with the appropriate skeleton, right? We're just talking about exponential functions, so we have this model to fill in. There's an a b value, and an x potentially, right? Barring some other conditions that they just say, change the labels, you know? It's basically this procedure. Right. You're first going to solve for a. Okay. And then, secondly, you're going to plug a that you get from doing that, right, to solve for b. Okay. Okay. Right. How do you solve for a first? All right, you plug in both ordered pairs. Okay. Well, let me just use one of them for the moment. Sorry, let me just specify this. You're going to use both ordered pairs eventually, but not immediately. Choose one or the other. All right. If this is, we're going to call this y for right now. Y equals a b to the x. Right. Let us say that we take this one and substitute it here and here. So the x value would be -2. And the y value would be 6. We're going to get an algebraic expression, not something that's purely numerical, because we still have the value of b here. Plug in one ordered pair. Then we'll rearrange it to solve for a. Okay. What would you get? If you had 6 equals a times b to the -2, what happens when you have a negative exponent? Realistically, what that means is that you have b sitting down here as an exponent of 2. And once you've moved it, it's no longer negative. It's accounted for. It's just a different notation, if you will. All right. Now to solve for a, you would have to move b, right? What is the opposite of dividing by b squared, apparently? To multiply by b squared. You do that here and here, the b's would cancel. And in this instance, temporarily, you have a is equal to be conform to good etiquette, pinky in the air, 6b squared. Okay. In this instance over here, right? You're going to plug in the other ordered pair, whichever one you didn't use. And also A. So if again this is your model, y equals a b to the x. Let's take these two and put them here and here. So there would be a 2 here and there would be a 1 here. And then we could take this half of what a is and put it in there. Sorry for the sloppiness. So a is really 6b squared. Okay. Now we have just one variable. We could solve for b definitively. All right. To clean this up because it's a mess, this would be 1 is equal to 6. All right. If you have b squared times b squared, as long as they're the same bases, you could apply the product rule for exponents, which means add these. You'd end up with b to the 4th. Okay. All right. Now rearrange it to solve for b. Divide by 6, divide by 6. And you have a similar situation to before, which is that you have something raised to an exponent, and we need to solve for just b, not b to the 4th. So we're going to apply opposite operations here. What is the opposite of raising something to the 4th? We could apply its reciprocal here, 1/4, 1/4, and then do it to both sides to compensate. Right. When you raise an exponent to its reciprocal, it cancels essentially. And then having done all of this, I'm sorry for the mess, this is what b is. B is actually whatever this value is. 1/6 to the 1/4. You could use your calculator for that. All right. In which case, again, do it very quickly. 1/4/6, rather than stylistically, aesthetically pleasant, to 1/4/4. It would give you the same amount. Okay. Probably going to have to round this, but so be it. Right. 0.63894. Right. We'll just go with the first 4 digits. B is equal to 0.6389. Save that. Okay. And now we have a third step here. We're going to back substitute into A. So I need to erase this, unfortunately, but that's what we'll do. Third, back substitute. To find A. Rather than before, we solved for A, but we got an algebraic expression. What we need to now do is get an actual number for A. So, if we had decided that this is what A is equal to 6b squared, and we just got a b value, we're going to back sub into that. So you can enter this into your calculator, 0.6389. I hate rounding in between, but so be it. Being a bad significant digit dude right now. Going to math hell later, I'm sure. You could use these very precise digits here. Of course, this is probably an approximate in and of itself. How many digits is that? 10 digits, you know. For the sake of consistency, I'm going to just type what I have, 0.6389. 6389, close parentheses, and it's squared. 2. All right, so you should have something like that. And I may have 2.4491, whatever it is. So 4 digits is good. Past the decimal point, I mean. So 2.4492 approximately. All right, now we have an actual value for A. We have an actual value for B. We're going to insert them in the skeleton now, in the model. Insert. So, 2.4492 sitting next to 0.6389. To the x, because this is a generalization, and you have that. Okay, and you could plug this into your calculator, and it would draw for you. Right. You will always get a more precise answer. I should say more accurate. Right. If you use a fraction, so you could preserve this. Right. While you're trying to calculate, it's just going to get messy. Right? This is just for the sake of simplicity and rounding a lot. Okay. I feel that I owe it to you to summarize that process. So I'll just write it here. Right. As I said, first, right, you're going to plug one of the x and y's, one of the ordered pairs, to solve for A. All right, just realize that this is going to be an algebraic expression, not a number. Number 2. Oh, my phone is about to die. That's not cool. Plug the other coordinate, ordered pair, x and y, and the A algebraic expression to solve for B. And then back substitute to find A, that is A as an actual number. Okay. Okay. I have to plug my phone in, so let me do that. Forget it. I don't want anyone to call me anyway. So what? So what? Well, it'll only be a credit card company, I'm sure. I never get a love letter or a phone call. Like, I love you, Francis. Here's $1 million. And that would be cool. One of these days. All right. One more of these. If you had to write a function now, give it a graph. function, an exponential function, given the graph. And I'm not going to pull out the graph paper board, but I'll draw you this picture, because it's really all you need. If you have an exponential function, that is exponential growth at least, you would have a shape that looks like this. It may be shifted up or down, but it's basically a curve of this sort. Okay. Again, what is key is to isolate what is the y-intercept here. Look for this. Right. Remember, that's the y-int. So that's whatever the a value is, right? You're going to borrow that. Right. Here's our model once again. A times b to the x. If I told you that this point was 3, meaning that's 3 there, right, up the axis, right, then immediately you could put a 3 here in the model. I'm going to instead call this y, because it makes it more useful. And I'll remind you of something else. Okay. We have now that same situation where we have 3 variables, right? And we can't really solve for one as an actual number unless we get it down to 2 of them filled in with another ordered pair. So what you would need to do is a second sort of little visual here is to look for a second coordinate, a second xy, a second ordered pair, right? If it was on graph paper, it would be a little bit easier to read increments, of course. All right. I'm going to cheat, and I'm just going to tell you the point here. So let's say that this is at the point of, wow, that's a really bad scale. Over 2x up 12. All right, so this point will be 212. Right. You would then insert a 2 here and a 12 here and solve for b. Okay. How do we do that? Isolate b by moving 3. If this is 12 divided by 3, what is that really? 4. If this is b squared, how do you solve for b if it's being squared? You could pull the trick that we have, which is to use rational notation rather than radical notation. That would basically be raising this to its reciprocal here and here. But because it's squared, it's probably more familiar to you. Alright, to simply go, alright, well, what's the opposite of squaring? Square root, right? That's what a half is, right? Right. When you see a value raised to 1/2, that's known as rational notation. Right. When you see the square root of something, this is known as radical notation. Right. Anyhow, the features that would be the 1 and the 2 here would be, 2 would be the index that identifies the radical, and this 1 would be the other number that is the exponent on the inside, right, which you optionally could put on the outside if you like. Right. Anyhow, this cancels this, right, in the same way that this cancels this, right? What is the square root of 4? Technically, it would be plus or minus negative 2, so b would be plus or minus 2. We're going with the positive, okay? We want the principal square root. So to fill in our model then, b would be 2. Right. Do not combine the 3 with the 2 and get 6, because bear in mind this has an exponent. And one of them, and the 3 does not, it's a coefficient. So this would be 3 times 2 to the x, to make it a little bit more obvious. Okay? Now, there's a way to cheat, which I'll tell you only now at this point, right, which is to get your calculator to basically give you this without you doing any calculations. Right. Use this sparingly. To be able to do something by hand, generally a person has a greater depth of understanding if they can. They're not just pressing buttons. Anyhow, if you want to get your calculator to do the exact same thing, we have figured that this is what the equation would be for a graph like this. Defined with the TI 83 or 84, whichever. Right. You need to enter, still the same situation. You need 2 points minimally. So you're going to press the stat button on your calculator, and then you're going to scroll over to edit, I believe it is. I haven't done this in a while. Stat. Yep. Well, edit is already there. Choose edit. And then you're going to see 2 lists. There'll be several actually, but you're going to use L1 and L2. Right? You're going to pretend that L1 is the x values, right? And that L2 is the y values. And since we have 2 coordinates, we're going to rip out the x's and list them. And we're going to rip out the y's and list them. All right? And you'll see something that looks like this. Okay. Okay. So here, I'll walk you through the process. Right. There's the stat button. It's already on edit, so you're gonna hit enter. Now you ideally would have some blank lists, right? So in list number 1, you're going to just type the x values. Right? So bear in mind, this coordinate is an x0, and this coordinate is an x2, right? And this would be a y, and this would be a y. Put them in order. Just simply type enter 0, and then you could move down, and then you enter the other one, 2. And now you have sorry. And now you just have to, ideally you would have more points, but this is the minimum, you need 2. Right? Now I'm going to put 3 for this point here, and 12 for this point here. Forced perspective, right? Something like that. All right, and there you have it, 3 and 12. Okay. Now, go back to stat, all right, and go over to calc. In this, you're going to see some choices. You want the one that is exponential regression. Down this list is exponential regression. You're going to hit enter. And you could tell it choose from L1 and L2 if you had something else typed elsewhere, but it's preset to just go for the last things that you did. So it'll give you this information. All right. You enter your figures 0, 2, 3, and 12. Then you go back to stat, scroll up to where it says calc. All right, go down the list to where it says exponential regression. And what you see on the screen is the information that you would need to flesh out the original model. So if this is our model, f of x is equal to a dot bx, okay? What you see is the calculated incarnation of this, which is y, right, is equal to a asterisk b to the x. All right, and it will tell you list a and b. All right. It'll tell you a is 3 and b is 2. All right. A is 3, b is 2. Right. The other information that you see that's r squared, right. R is a correlation between what is predicted and what is observed. Right. It's from statistics. And r squared is basically a percent of variation. Don't worry about that. Anyhow, you could just take out these two pieces of information and then write them yourself, right, like so. You just have to brute force enter some points, right? Now that would be useful if you were in not only statistics, of course, but if you were in maybe a business class or a science course, and you were trying to make a model to predict, profit or something like that. In the long run, you just minimally need 2 points. Okay. It's cold. All right. Now we get into some theory. Let me draw you a picture again. This is more theory than anything else, but it's a nice overview as well. If you can imagine this as being a number family tree. The types of things that we deal with, right, are either real numbers or imaginary numbers. And primarily we're concerned with real numbers, right? Of the imaginary numbers, immediately, there's the most basic type. The square root of -1. It's a famous imaginary number. We just call this the letter I, oftentimes. Of the real type, right, there's some subcategories. We have rational numbers, and then we have irrational numbers. What's the difference between them? Rational is something that can be a fraction, essentially, whether it's a decimal or not. Could be terminating, could be repeating. What is irrational can't be a fraction, because it is non-terminating and simultaneously non-repeating, as a decimal at least. And there's a slew of famous irrational numbers. They're the more interesting of the numbers in general. All right. Famously, there is the square root of 2, which would be, I'm just going to put a couple of digits here, 1.4142, something into infinity, and pi, 3.14159, whatever it is. Well, these things, square root of 2, which preserves all of that infinity of non-terminating, non-repeating digits, right, is a better summary than the decimal. And similarly, the pi symbol is also a better summary of the entirety of infinity, since we'll never see the end of it. So often we would just celebrate and keep these two things, the square root of 2 and the square and pi, to add to our list of interesting things. There's one interesting thing, a second, and a third. Well, there's a third famous irrational number, right? And it's the subject really of today. It is E, right? E is 1.7172 something. No, sorry, 82. Shame on me. 82, 81 something. And this is basically Euler's number. It is just coincidental that it is an E, and the person who is famous for this number is the same, right? But he didn't name it after himself, right? He just chose E, right? At least that's what I've been taught. Yeah, and preserving, someone's, good name. Anyhow, save these, right? The square root of 2, pi, E, and I are all in math world the most popular superstars. I've heard someone say that, and I like that. I think that's cool. The superstars of math, the irrational numbers and an imaginary number, the most basic imaginary number, right? Interestingly, oh damn it! Sorry, forgive me. 2. Oh God, for shame. Going to math help for sure. All right, it's 2.71. Sorry, not 1.71. Thinking of that. 2.718281. Something else after that. These are all non-terminating and non-repeating. These things, square root of 2 and pi, are ancient. Right? These come from geometry. Geometry, like arithmetic, is a rather old form of mathematics, right? Even at a point in history when they weren't using Hindu-Arabic numerals, like 2 was an Hindu-Arabic numeral, right? A better system, right? The Greeks knew this number, the square root of 2, right? And they also, like Archimedes famously, was looking for better and better approximations for pi, all right? Hence the Greek character, right? They're old, all right? I is probably medieval, right? And it comes from algebra. This E, on the other hand, where does that come from? Well, it's more, I think, forgive me for my lack of history, but I would call this modern, Modernity is at least from, say, 1500 forward, not contemporary per se, neoclassical. I'm probably confusing this with art class, but anyhow, let's just call this modern, all right, rather than medieval. This comes from finance. Right? Money, right? Capitalism basically produced this. All right. Let's discuss how to get this. Okay. All right. In the packet that I had given you, there's this sheet. It looks like this. I'm going to just do this one time just to show you how this ends up working. Oh, you know what? Just for the sake of it. There's famously, you're not responsible for this, but I think it's cool, right? There's Euler's equation. There's a Swiss mathematician. He's famous for a lot of things, but this is Euler's equation. And the reason why it is very interesting is because it incorporates all the coolest numbers. All the coolest numbers of math, right? 0 and 1. What could be more fundamental than them, right? And those are just regular digits, right? E from finance, right? I from algebra, right? And pi, right? The only thing that's lacking, I guess, technically, is the square root of 2. But we're still covering geometry, algebra, finance, and basic arithmetic all in one equation. That's cool, all right? Euler's equation. Let me erase this because I need the space now. if you humor me, all right, there's this table I had given you again. It looks like this sheet. All right. I'll just draw this very quickly. I'm not going to torture you, but to give you an idea of how we've arrived at this, right? We, you know, like I did it. I wish. Input. Output. Remember, brute force works for a lot. And it's going to work in our case again. Let's say we have x as an input, as we typically do, and we have a function of x that looks like this. 1 plus 1 over x to the x. We have x as an input here and also here. If you, and I'll do this just very quickly, were to, and it's kind of a fun exercise, I swear. Right? Just as before, if you start, you can't use 0 because you know what's going to happen. Math hell, right? That will be undefined. But we'll go to the next digit 1. If you insert 1 here and here, what would this end up being as an output, a y value essentially? 1 plus 1 over 1 is 1 plus 1, which is 2. 2 to the first would just simply be 2. That one's pretty easy. Right? If you use 2 as an input, and you put the 2 here and the 2 here, you'd have 1 plus a half is 3 over 2. Times 2. Right? And then you'd have to square both of these, right? Which means that you'd end up with 9 over 4, which would be 4 goes into 9 twice, and a quarter, right? This would be 2.25, if you like it as a decimal. Right? If you use 3 here and here, you have 1 1/3, which is really 4/3, and if I add those, and then you'd have to cube it. And you'd cube the top and you'd cube the bottom, and you get 4 times 4 is 16 times another 4 is 64 over 9, right? And you'd end up with a lengthy decimal, at least it's getting longer and longer. What would eventually happen is you get a repeater. I believe that's right. Let me see. What's 1 plus 1/3? 1.3 repeating. Yep. Raised to 3. Yes, you end up with this. Something's up. 64. Oh, I'm sorry, wrong number. It's 27. That would be why. Okay. Divide these two. 64 divided by 27. What do you get? You get a repeater. 0.370 repeating, bar notation for that sake. And it goes on and on and on and on. Right? Eventually you get down to, you notice in this list, if you really feel compelled to try it, right? You can input 4, you can input 10, 100, 1,000, 10,000. What you eventually start to see is that by the time you get to, you know, at least 100, right, is that this number that keeps showing up is 2.7 something, right? There was a mathematician, Jacob Bernoulli, a little bit earlier than Euler, right? So he lived in like the 1600s, say. He was working on this, right? And he knew that there was something special in between hole number 2 and hole number 3. It's this number. It's really Euler who is the person who refined this. And incidentally, this is a very simplified version of the compound interest formula. Because again, this comes from finance. 1700s. This is Euler who simplified it. All right. And he figured out that with a great deal of precision that it's 2.7188182, whatever it is, into infinity. Right? A special number like pi, right? Like pi is between, somewhere, if you want to be very vague, right? Between 3 and 4. Right? Well, this is how you would get to that, basically. It would approach this 2.71, all right, the more inputs that you use. All right. I'm not doing it any justice, at least not what it deserves, right? But this is E, right? That number, that special number that exists between 2 and 3. And again, it comes from finance. It comes from the compound interest formula, which looks like this, right? A very simplified version of it, okay? It nonetheless has this graph. All right, if you drew this exponential function, it looks like this, using E as a base as opposed to something else, it would have a similar graph. Yeah. We've had this to this point. The function of x is equal to, again, a, b to the x, right? If we substitute E in here, and a slimmed down version of it, let's just call this y equals e to the x, it would produce this very similar looking graph. Where you have a curve that curves up like this. And it goes through a y-intercept, which is going to be, because I didn't put an a value here other than 1, it goes through 0, 1, right? And the next interesting point a little bit further over would be at 1, and it would be e, right? 2.7 something, you know. So it would be perhaps a slightly sharper curve than say just 2, because what number is it really? It's 2 point something rather than whole number 2. It'd be a little bit more steep. I'm getting cold. Oh, it's not good. All right, let me introduce you to some more applications. So I'll give you an overview, and then we'll do a word problem again. We'll probably, as I mentioned earlier, revisit this in chapter, I think it's chapter 6, but it'd be like section 6, 7, something like that. Here are some applications for non-linear growth and or decay. I have very limited real estate here, so I will try to be a little bit concise. Right. Famously, you know what, I have to do sort of a scaffolding here so I don't overspend my room, the space that I have unfairly. I'm going to draw a simple table here. And try to chop this up nicely. be 4 applications at least. All right. There is, to start with, population can be calculated. It's a non-linear sort of growth or decay. It would be a growth usually. Compound interest is the thing we were just discussing. Mass of a radioactive substance. And something that's a generalization, continuous growth or decay. These are all formulas, which you can use at will. The population formula would look something like this. Since it's a function, you'll see it written in function notation, P of t. And then you'll see these features, P naught 1 plus R, I like to use a capital letter in this case, T. In the case of compound interest, you would see this a lot of times. Again, in function notation, A of t is equal to P naught 1 plus R over N, and then raised to an NT. And actually, if I had any sense at all, what I would do is stick with the color. So I'm just going to rewrite this, but I'm going to write it in green because I'm trying to be consistent. It's about money, right? So green. It's a little faint. I'll use the swap for a different color. Textbooks will use a lowercase r very often, but unfortunately, because of handwriting, and I have to do this by hand right now, I don't want you to confuse a lowercase r with a lowercase n, right? Because they are actually different things. And this is a fraction that appears in this formula. Okay, so this is supposed to be an r. Trying to make it obvious. Mass of a radioactive substance is similar looking. It's labeled A of T, and it's a little less complicated. It would be T time over N. I'll tell you what the parts are in a minute. The generalization of continuous growth or decay is similar to mass. And this is A to the E or T. Now, having gotten all of those out of the way, let me tell you what the parts are. To summarize. Okay. Bear in mind, this is function notation. All right. So what is it? It's population as a function of time, right? P of t. Compound interest is basically an amount of money as a function of time. The mass of a radioactive substance would be mass as a function of time. And then the continuous growth or decay using E as the base in this case is just a generalization. This is in general. Right. What do the individual parts mean? Right. And you could, if you want to, you could just opt for just P in this case, or just A in this case, or just A again, or just A again, capital. Right. The P with a subscript of O, you might say naught, right, is the initial population somewhere. In this case, it's just a weird coincidence, right? The p-value here is an initial amount, just like in the generalization. A is an initial starting value, right? But it actually stands for principal. Right? In terms of money, that means an original amount of money. Somehow. Okay, I'm using dollar sign just to signify money. I should use, something else perhaps, but same thing here. Now, if it's A naught, right, it's just the original mass of something. So you might say initial mass. So many kilograms. And as always, A in general is just the initial value. Something that is a starting value, starting point. Okay. The next thing that is consistent is time, really. I'll put this in red just because it's a little bit easier to see. T in this instance, T in this instance, T in this instance, and this instance is all T for time. Right. Just has to be in years. Okay. T is time. T is time. T is time. Right. After that, there is some similarity between a few of them and not all of them. All right. And again, don't bear in mind this has to be years. Okay. Let's discuss the R. All right. The R, which I have capitalized, a lot of times again it's just lowercase. I think it just stands out a little bit more obviously. Again, I don't want you to confuse it with this N value. Right. And it's only 3 of these things that have an R. Right. An R just stands for a rate, right? Which realistically is a percentage, a rate of change. The rate of population growth, the rate at which something is compounded, compound interest. It's a percentage. Let's see. This also has a rate, so I'll put it here. This is a rate. Bullet points here. Alright, as for the N, that varies. I'm going to go back to black because I think it will be easier to see. The population formula does not incorporate the variable N. The first time that you would see it in my diagram, at least, is in compound interest. N, lowercase, is the number of times compounded in a year. N is also used in this case. It has a different purpose though. Right? N in this case is the half-life. a substance. That's basically how long it takes to reduce to half. The original mass. And then that's it. Right? There's no other ends. There's just an end here and an end here. Eventually what I want to do is I want to make a table that's a little bit less messy. And if I can, between now and a couple of days from now, I'll mail it to you. Right? But I just want you to be familiar with the compound interest primarily, because we were just talking about E, and that's where E comes from. Now, insofar as growth or decay is concerned, population is an example of growth usually. It doesn't have to be, it can be decay. Compound interest is also growth. All right. Mass of a radioactive substance is typically just decay, right? And there's a half-life figured into the unique substance. It varies between substances. Like, I don't know off the top of my head, but something like uranium or plutonium would have different half-lives, all right? The amount of time it would take for the substance to reduce by half to not being uranium anymore, or plutonium. And this is a good general formula. Right. As you can see, it has a lot of the same features as what we're familiar with. It's really just changing the function notation here. All right. There's an initial value. There's some base. All right. In this case, there's a percentage that you could fit into here as a sort of a coefficient of time, and then time itself. All right. In all instances, time has to be in years. Now I'll do an example with you. If again you look through the packet of materials, here's a word problem to figure out compounding interest, all right, in different scenarios. We'll do that. Rebelling. Stop. Pressing too hard. What happened? You know, I lost my protractor a couple of days ago, and I have this sneaking suspicion that I know where it is. Once I clean this, I'm going to move my board a moment and see if my theory is correct. Alright, my markers off the floor. And that'd be all. Let me just move this for a moment. We have a vice grip here, which is not doing its job. We failed the Walt. Just dirty. Alright. That is really ferociously gross. Yeah, there's no cleaning it now. Right. Perhaps I can turn this around. No, that's not good. My wood is warped, so it's not really helping me. You know what? Bear with me. Let me just clean my little gutter here. This is all felt from the markers. I gotta clean that. I'll be right back. I gotta throw out this fuzz. Put back the parts here. Warping. Okay. found my protractor. One of these days. Sorry for the technical difficulties. I don't know why this is being so stubborn today. I think it's the cold weather. As I'm in my hallway, this is a staircase where I'm working right now. So it's a bit cold. Alright, I might have to modify that later, but I'm not doing it now. Alright, perhaps. No, I'm not gonna get a good grip on that. Suffice. Good. I'm gonna have to buy another vice grip, I think, but okay, later. Get back to work. Okay. I was wondering why my markers kept falling all over the place. That's why my wood is warping. I made this out of plywood. It's just to make it tall enough. Anyhow, if you take a look at this sheet, we'll do this example as a problem to go through the process of considering compound interest. All right. Remember, E comes from compound interest. Unlike pi and, square root of 2, which come from geometry. Right. And compound interest is the formula we were just talking about. It looks like this. A of t is equal to P times the quantity 1 plus r over n to the nt. Now, a couple of things. A lot of times in word problems you hear these phrases thrown around. You've heard about APR, right? Annual percentage rating. Annual percentage rate. Right? This is a percent. Whatever percent is quoted to you, this is something that is calculated on either an investment which is ideal, or a loan. You poor folks who, like me, have many student loans, right? You have an APR that you'll be paying for the rest of your life. Right? Not to talk you out of an education, because I still do believe in that. I just think it should be free. Right? The investment is a percent, this number is a percent, the annual percentage rating, either on an investment or a loan. When you use it, you have to either convert it to a decimal, right, or a fraction, right? If it's a percentage, it's something over 100, which makes it easy to use as a fraction, okay? Now, if you hear this other phrase, nominal, that sometimes is what they refer to APR, the rate. referring to the rate. All right. It means that it is compounded more than once per year. Blue is misbehaving now. Yeah. Nominal rate refers to the rate, just the APR very often. It means that it's compounded more than once per year. This is a bit faint. So let me darken that up and I'll try to clean up the mess here. Per year. Now what does it mean to be compounded? Right. Compounding is basically reapplying something in a calculation. So if you've probably heard of simple interest. Simple interest is multiplying three numbers, the percent, the original amount of money, and time. All right, but it just happens once, the calculation, and that's it per year. All right. If you have something that's compounded interest several times through the year, the value of money, which is growing, right, will be reinserted into the formula, right? When you compound something, you're reapplying it to a calculation. All right. So it actually, if you were the person who is, lending money, like a credit card company, all right, or a bank, it's in your best interest to use compounded interest versus simple interest. All right. Anyhow, this word problem will illustrate that point. All right. Here's our formula. All right. And if you read this. If you invested $12,000 at an annual rate of 3%, right, find the balance, right, after 5 years for each type of compounding, right, quarterly, monthly, and continuously, which is a different formula actually. All right. If you use this formula for compound interest. Jeez, that's a terrible marker. Right. Quarterly. Right. Let us think about how many times this is compounded quarterly. How many times per year is that? If something is quarterly. That implies that it would be done 4 times per year. This is 4 times, right, in a year. So if we run the calculation, given the information of $12,000 invested and 3%, and that it is quarterly compounded, all right, we're just going to have to fit those features into certain places in this formula. All right. Incidentally, why call this A of t? A as in account, balance, like a bank account, all right, as a function of time. So remember the features. N is number of times compounded. In a year, right? T is just time. And R is the rate. which realistically means the percent that's quoted to you. This is misbehaving now. Okay. So I'm going to simplify this, all right, and then I'll superimpose the numbers that we're going to use for that. Okay, if we just call it A for account balance, rather than, we know it's a function. All right, P of O, P naught, 1 plus R over N times NT. All right. What's the original amount of money that's quoted here? $12,000. Right? Would be sitting in place of P of O, P naught, because that's the principal, the original amount of money. The OG cash. Okay. Principal. Okay. The rate is 3%. In this case, it's 3%, right? What is that as a decimal purely? Right? 0.03, right? Remember, if it's a percent, that means that it's really 3 over 100, and if you wanted the decimal, divide 3 by 100, you get 0.03, right? The number of times compounded quarterly is 4. So you would stick a 4 here and a 4 here. And then there's the last thing. It was asking after 5 years. All right? So you would put 5 in place of t here. All right? You could plug, as long as you're careful with parentheses to make sure that they are where they belong. Maybe simplify some things, like that's 20 really. All right, you could type this into your calculator. All right? And what you would end up with is, you'd probably have to round, but do remember it's money, so round to the hundredths place. You would get something like this: $13,934.21. All right, that's quarterly compounded. Okay. Just for the sake of space, I'm going to erase this. If you did the next portion of the question, it would be do the calculation again, but if it is compounded monthly. Okay. If something is compounded monthly, that means the calculation is done how many times per year? How many months are there in a year? All right. This would be 12 times. So in terms of this formula, it would be 12,000 times the quantity 1 plus 0.03 now over 12. Right? And it would still be 4 here and here. Well, now it's 12 here. Right? And the time would still be 5, I should say. If you entered this into your calculator, and I would simplify at least that to 60, right? Just be careful with the parentheses. You would get this approximately. $13,939.40. Not bad on a $12,000 investment. You paid almost $2,000 extra by the end of the year. Okay. You can see that if it's compounded 12 times versus 4 times, it's a little bit higher in amount of money. This is $39 versus $34. Now, if you did it quarterly, continuously, you need a different formula. All right? We want to use the continuous growth or decay formula, which means that we would use this instead. is equal to AE RT. The initial value that is not calling it with a subscript P is still 12,000 using base E instead, and then the rate is 0.03 times 5. So you could enter this in your calculator very carefully, right? Make sure that you realize these are both in a subscript, pardon me, a superscript. So if you want to, you could calculate as 0.15 realistically. Let's see. What would you get? You'd get about $13,942.01. Okay. So that's the best deal of all, compounded continuously. Okay. All right. At least if you're the person who is investing, right? Now, what I'm going to do for section 6.2 and 6.3 is just give you the transformation models, right? And just tell you what the parts do. All right. Let's see if my phone is dead yet. No, almost dead. Back you go. This is going to be fixed. Let's see. All right. To summarize, there's this sheet. Right? This is the transformation models for exponential and logarithmic. All right. This is material, just to acquaint you with it, from section 6.2. Right. Here's our transformation model. Right, we're just adapting. The transformation model, right, for exponentials. Right. Was sometimes we're going to do that today. I should put this here and not think about it anymore. If this is a model for transformation, you know by now, right, that each one of these positions in this model has a job. Right? You know that this causes reflection, meaning it flips. This causes a vertical stretch, right, or compression, depending upon the number. This causes a horizontal stretch or compression, depending upon the number. And these two cause shifts. I'll just be more specific. This is a horizontal shift, and this is a vertical shift. Well, if we adapt this to exponential function, it's going to look very similar, and it's going to have similar jobs. Right? It's going to be the function of x, right? But it will be, look like this instead. Plus or minus a, right, times b. And then in superscript, you would see this, x plus c, and then plus d. Okay. Now, what is the same? For whatever reason, we've moved away from using h and k, and we've gone to c and d. But basically, this is the vertical shift, the d value. Okay. This is the horizontal shift. and this is the vertical reflection, pardon me, stretch or compress technically. And this causes reflection just the same. Now, to summarize this, here's this table again. When you're working these, if you were going to do it by hand, and you're realistically not because you have a calculator, right? This is probably a good order to work in, right? If you horizontally shift something, you are dealing with basically the C value here, right? Just realize, once again, the horizontal shifts are counterintuitive. So if you see, as in the case of H here, a negative value, you're going to go right. If you see a positive value, you're going to go left. It's weird, right? It's counterintuitive for those. The vertical shifts are, thankfully, this is intuitive. Meaning what you expect is exactly what happens. You see a positive, you go up, right? You see a negative, you go down. All right. In section 6.4, you would have this adapted for logarithmic, which we didn't really talk about yet, but I feel it's more appropriate to mention now. Right. The logarithmic function, this is exponential. The logarithmic function would look like this. F of x is equal to plus or minus a log b x plus c plus d. Right? It's more similar to the exponential model, just insofar as changing these letters to c and d as opposed to h and k. All right. This is again written on this piece of paper. Right. If you look here, this is the general equation for all translations. This is the transformation model for exponential functions. Right. This is an exponential function. This is what the transform model could potentially look like. This is a logarithmic function. We're going to get into that in a few minutes. And this is what the transformation model would look like. Okay. To be a good sport, let me clarify some things. All right. That's the material from 6.2. This is the material from 6.4. I'll make another table because I think it might make it a little bit more clear. That's dirty, man. Oh boy. All right. Let's see. The letter C, all right, whatever number is sitting there, is the horizontal shift. All right, so whatever is sitting here, that number. All right. Remember, it's counterintuitive. When you see a positive, move left as opposed to what it would normally be. All right. Plus is left. Negative is right. D is the vertical shift. And that one is perfectly intuitive. You could think of this as also the horizontal asymptote. Right, for the graph. So ordinarily the horizontal asymptote is y equals 0. Right? But if you have a number here like +3, the whole graph is going to be vertically shifted. So the horizontal asymptote in theory would be shifted as well. Okay. A is a vertical stretch. Right. If these conditions are met, if the absolute value of A is greater than 1, and it's a compression if the absolute value of A is between 0 and 1. In other words, if this value A here is a fraction, it's greater than 0 if it's a half, but it's less than 1, it'll cause something to vertically compress, so it will be squashed. Right. If you have a negative up in the front of A, right, that causes a vertical reflection. That is, you might say, about the x-axis. It's going to flip. And if you have a negative value as part of that x next to B, this will cause a horizontal reflection. That is about y axis. See if that's in the frame. Sorry, it's kind of dirty. The rule of thumb is if you were going to do this by hand, and realistically, again, you're not. You're going to probably be using your calculator. But if you were going through that exercise, you want to follow the order of operations here. What does that mean? It means you would pay attention to exponents before you would deal with something that's addition and subtraction. So realistically, what that means is that you would do this first, and you would do this second, that transformation, and then this third, and this most likely fourth. This does not come up too often when you have a negative here, but it is technically part of the exponents here. So you might do this 1.5. You can make this the 0th rule. Okay. Again, this is summarized, at least on this handout for logarithm and exponential transformations. I stole this from the textbook, it's a nice table. All right, but I'm just trying to, if you were going to do this by hand again, I'm trying to give you kind of an order. All right, now as for the log function, all right, let me just take a color here. Let us say you started with C, all right. This is again a horizontal shift. All right. This is again a vertical shift. And that's still counterintuitive. A is the vertical stretch or compression. Conditions are slightly different. It's a vertical stretch if A, well, this much is the same. If A is greater than 1. But it's a compression if it is just A, absolute value A is less than 1. Okay. If again you have a negative up in front of the coefficient, A, then this is a vertical reflection. And if you have a negative attached to the x, this would be a horizontal reflection. This means to reflect about the x-axis, this means to reflect about the y-axis. This is about x-axis, this is about y. See if that fits. Okay. I don't know if this has to be conformed strictly to the order of operations. I think because it is not exponential, you can get away with doing something a little different. Might try it this way. Might do, let's see, try this first if you're going to do this by hand, and this second. Let's see. Maybe this third and this fourth. My instinct is that you should do the inside of a function, you know, deal with that first, but I don't know if that's bad advice or not. You really only know unless you play with it. Let's see. I don't want to give you bad information, but this is what my instinct would tell me to do. Right? If I were going to try it by hand, right? This is really, I definitely would do it in this order, right? For this particular type. This one, I'm debating, right? So, try it this way, right? If you want to do that for practice, you're not really obligated to. Right? Let's see, vertical structure. can't, with a clean conscience, say that you should do it that way. All right, you can try it, but I'm not obligating you to. All right. All right. These are the effects. All right. In this case, again, I would do it in this particular order. You should follow the order of operations. All right. If you were to follow the order of operations in this case, it might, because it's part of the function here, log, you might get in trouble. All right. So, insofar as this is section 6.2 and this is 6.4, I'm not giving you homework from these. All right. These are just to illustrate what the effects are. You would use your calculator at this point in the conversation. Okay. What I'm going to do now is section 6.3, that you are responsible for. There goes my phone. Okay. This is more my favorite thing. I really do love logarithms, actually. All right, let us do finally, after all this time, section 6.3. All right, what is a logarithm? Logarithmic functions. As I had mentioned from before, there are these two new functions, right? There's exponential and there's logarithmic. And these are inverses of each other. Which is why, if you actually wrote them out, instead of in function notation, which is more likely the way you would see it, in a simplified version of the exponential function that is not worrying about the coefficient here, it would be y is equal to b of x, right? Versus in function notation here, no, I'll just stick with this. I'm really gotta clean this board. All right, if you had the obvious inverse of this, x would be b of y, right? B to the y. Right? They don't choose to write it that way, even though this is correct. Right? Remember, when you have inverses, the position of the x's and the y's would really be switched, at least if there isn't any other extra features here. All right. Now, the preference is to still rearrange this to set solve for y. Right? Which means what you're going to get is this, right? Rearranged, you would get y equals the log of base b of x. Even though you will see this, realize that it means this. Okay? Okay. And then, of course, they'll put it back in function notation. I'll call it, no, it's the function log b of x. Right. And incidentally, that's how you would read it. Right. Right. If you're going to read this out loud, you would read it as log base b of x when you see something like this. And if it's part of an equation, you would say is equals y. Right. Now, if you're wondering, geez, you know, of all things, why this word, right? Why log? Why don't you just say inverse? You know, that would have been maybe more intuitive. This comes from a guy named John Napier. And John Napier was a Scottish mathematician. He lived in, was it like the 1600s or something like that. Anyhow, when you went to college in those days, at least in Europe, right, you were guaranteed that you were going to study Greek and Latin. So a lot of times the people at the time, the most famous math people and science people, they incorporated what they learned from their other classes into whatever they were doing. So he combined basically these two things from Greek, right? Logos and arithmos. Logos, in a certain context, is referring to a ratio. It really would be logic or reason would be a better translation. More better. Yeah. Arithmos means number. Right. So if you see a logarithmos, a logarithm, right, it means literally a ratio of numbers. Now, normally when we think of a ratio of numbers, right, we're referring to a fraction, right? Something that has a top and a bottom, a numerator and a denominator, right? In a certain context, sort of stretching the definition of it, right? This is a bottom, if you will, and this is a top, right? So it's a kind of ratio, it's just not a fraction per se, right? A logarithm is basically something stacked on something else without saying that explicitly, all right? They will use this word log to imply that, okay? Okay. All right. Now, what you'll be asked to do is to convert and to evaluate. All right. Eventually, what we're going to get into is logarithmic properties. All right, but that's Thursday, basically. Right now, this is just introducing the concept, so it's just to get your feet wet. A lot of it is not too bad as long as you get used to the procedure involved. I am going to seriously wipe this down with alcohol now because it's getting really dirty. Another kind of spray over. All right. I have to get another napkin in a minute. Okay. Susan's behaving too. That will suffice. That's a little bit better. Okay. if you are just converting from a log to an exponential form, this is going to sound silly, but I really do mean it. This is kind of the idea. Draw a jelly bean. Right. Right. Read counterclockwise. You'll see what I mean in a moment. Here's an example. If you had the log base 3, right, of 9 is 2. Right? What this really means, and this is the jelly bean, right? It really means 3 squared equals 9, which I don't think anyone would disagree with, right? You read this counterclockwise. 3, 2 is 9. All right. Here's another. If you had the log base 6, and you notice that I'm kind of arbitrarily not throwing parentheses in here. I prefer to do that for functions, but you know, it isn't always necessary. Equals a half. All right. Again, draw a jelly bean. And read it counterclockwise. 6 to the 1/2 is equal to the square root of 6. Right? This is another instance of having something in rational notation versus radical notation. Okay. The index, although in the case of square roots they never do it, you would put a 2 there, you put a 1 here.
Can we get some more
Paper towels. That good. Okay. This is much more efficient, but unfortunately uses up a lot of alcohol, which is not easy to come by either. Not in Corona world. Very hard to get rubbing alcohol. Right. Now, if you were going to convert the other way, from exponential form to logarithmic form, here's what I would suggest. This is black, it'll be easier to see. A couple of things to think about. The base is always the base. Okay. So whether you see it down as part of log here, b, or you see it as b to something, right? It's a base. Right? The base is always the base. Right? What you're going to do is you're going to write as the bottom of log. So you're going to put it here. Whatever you identify the base to be. All right. opposite side of equal, right, becomes the argument. That is the thing that is written in parentheses. And the exponent is what is equal to. Alright, here's an example. If you saw something like this, 2 to the third equals 8. And you're translating this into something that has the word log in it. Right? Let us start with this. The base is always the base. So what's the base here? The base is 2, so you're just going to put it down there. All right? What it is set equal to becomes the argument. That is the thing in parentheses. And the exponent is the thing that it's set equal to now. Okay, let's do a couple of these because they're tricky, right? When if you've never seen it before, it takes a little getting used to, right? Do a couple up here. That erased very nicely. Okay. Let's see. If you had 5 to the third equals 125, right? And you're translating this into log something, all right? Remember, these are the voids that you have to fill in. Okay. The base is 5, all right? What is the opposite side of equals? 125 becomes the argument, right? And the exponent is what this is now set equal to. Right. And if you have to, you could always draw the jelly bean to verify 5 to the third should equal 125, which you read counterclockwise. Here's another. If you're going to hate green, let's see. 2, that's not too faint, it's visible, good. 2 to the negative 1 is equal to, looks like it's 1/2 here. Okay. This is going to be log, and we need to fill in these 3 voids. Okay. What is the base? It's 2. All right. The opposite side of equals is 1/2. That becomes the argument. And the exponent is what it's equal to now. And again, if you drew a jelly bean, right, you'd have 2 to the negative first is 1/2, which is true. Okay. There we go again. Let's do this again. Let's evaluate now. Evaluating is, for right now, because we're not solving equations that involve logarithmic or exponential functions or forms. It's just purely arithmetic, but it's a little alien, so it takes a little getting used to if you've never seen it. Tasked with evaluating. Boy, that's nice and dry. Right. What you probably want to do is convert to exponential form. first. And if you are given no letter, if you are not given equals a letter, some letter, make it so. Make one. You'll see what I mean in a moment. Okay. So here's an example. All right, if you were asked to evaluate, and that's really what this is. This is evaluating. Getting an actual number for an answer. The log base 4 of 64 and you notice that there's no equal sign. It's not part of an equation. It really is just an expression. For the sake of getting through it, what I would do is throw in that extra feature. This is what I mean here. If not given equals some letter, make it something. So I'm going to call this equals x. It could be any letter. It doesn't have to be x. It realistically should be y if I was sticking with the original program here, but I tend to like x personally. All right. So I'm going to draw the jelly bean now. Here's the jelly bean. 4 to the y is equal to 64. Remember, you read counterclockwise. You would now try to conceive, because you're going to do this by hand, all right? By mind, really. What is it that would make 64? Right? 4 to the first is 4. 4 squared is 16. What's 4 to the third? 64, right? Y would have to be equal to 3. Okay, let's do a couple of these. Let's see. All right. What if you had log? You're evaluating still. Base 3 of 1/27. Right. Notice that it's not part of an equation. Really, it's just an expression. So make it like that. Call this log base 3 of 1/27, and again, you could make it any letter that you want, so I like x personally. X is not really appropriate if you're just converting from, a function to another function. That's a function to its inverse, all right? But in this case, you can get away with it. So read this as 3 to the x, the green is failing, is equal to 1/27. Right. When something equals a fraction, what must be true of the sign? It would have to be negative. Right? This would have to be negative x in order to be a fraction. Right? To produce a fraction here. Now, insofar as the numbers 27 and 3 are concerned, again, you have to try to conceive of what makes 27. Well, 3 to the first is 3. 3 squared is 9. What's 3 to the third? 27. Right? So as long as x is equal to -3, we would end up with 1/27. It would have to be -3. There are two special log types. There's what's referred to as the common log, and then there's natural log. When you press this button on your calculator, it understands this situation. When you press this button on your calculator, LN, it understands this situation. All right. What's the difference between them? Well, a common log is the situation when it is base 10, which means that in theory it would look like this. No one ever writes this, right? But it would be log base 10 like that. If you have a natural log, it incorporates e. So this is base e. Right, and again, people tend not to write this, but it would be base e to some argument. Right. If it is necessary a little bit further down the road, for the sake of clarity, I would explicitly write that. Right. More often than not, what you would see is really this. Natural log and then whatever the argument is. They put an ln. I'm not sure why it's ln. It could be perhaps there's some French origin. Like I want to say Standard International System of Units, right? Is SI, right? Because of how it would work out in French. Well, perhaps natural log is the same thing, which is why L would be in front. Just a guess. Okay. Anyhow, if you wrote this as part of an equation, it would be y equals log base 10 of x, something like that. All right, and then this is in its logarithmic form, and in its exponential form, it would be x is equal to 10 to the y. Okay, I'm going to make this a little bit separated here. All right. Logarithmic form, exponential form, they're the same. Same. If you saw this as part of an equation, it would be y equals, say, log base e of x. Very unlikely, but in its exponential form, it would be e to the y, pardon me, I'll just make this x is equal to e to the y. These are really the same thing, it's just two different notations, if you will. Two different ways of writing it. One is the logarithmic style, one is the exponential style. Alright, now if you were using your calculator to do some other base than these two things, here's what you would do. If you're going to use your calculator to evaluate something specific that's not a base 10 or not a base e, right? Or any other base, there's a couple of things you can do. If you press the math button and go down the list, you will see this as a function available to you. If you select that, what you will see is on your screen it will show a box here and a box here. And you can enter whatever the base you want, whatever the argument. There's another shortcut. Instead of doing that, you can go through alpha. hit the window button. And what this engages is, I want to say function 2, is it? Yeah. Right. And immediately, well, what you'll see is choice number 5 is this, right? And this is what it will spit out. Years ago, you would have had to use something called a change of base formula. If you happen to have an old calculator, you may still have to do this. All right. If you want something that's a peculiar base that's not 10 or E specifically, you can get the calculator to still do what you want, right? But it's a little extra typing. The change of base formula is this. Whatever your base is, whatever your argument is, right? You could write it as a ratio. The log of A over the log of B. And it will give you that as an equivalent. Right? You don't have to use log. Alternatively, you could use the natural log of A. It's a ratio. This would work as well. That's known as the change of base formula. You probably don't have to go that route, but in case you don't have updated software, you're borrowing an old calculator, all right, this is what you would do. Okay, here's some just examples of where you might want to use a calculator. It's not impossible. Well, I shouldn't talk you into it or talk you out of it, but here, let's just do a couple of these. You could verify this with your calculator. Let's say that you had to evaluate the log of 1,000. Right? Just realize this is really log base 10 of 1,000 equals, let's call it x. Yeah. It really means that. So if you put this in exponential form, you could probably infer, right, what this really is. Right? It's 10 to the x, whatever that is equal to 1,000. Right? And you can figure it out. Right? And go, well, right, 10 to the first is 10, and 10 squared is equal to 100. 10 to the third is 1,000. Right? Number of zeros is what would be the exponent in the case of powers of 10. So x is just coincidentally 3. Right? If you press this on your calculator, I'll show you now. You just entered log of 1,000 here. There's a button. Let's see, where is it hiding? Here it is. Log. Notice the function notation here. Close the parentheses. You don't have to, but it's being good. 3. Alright? Why? Because it really means that, and it's figuring out what the exponent would be. It's 3. Here's another one. Evaluate this unique log, log base 5 to the cube root of 5. Again, if there's missing information, like this is not, again, it's just an expression right now. Right? If you converted this to an equation, I happen to personally like x, so I'm going to use x there. Okay. I can then convert this to exponential form. Draw the jelly bean. 5 to the x, whatever that is equal to the cube root of 5. Right? I I may have to go, fiddle with the notation a little bit. Once again, this is radical notation. Radical, man. If I convert radical notation into what it would be in rational notation, there's a 1 really here. This is the index. This is really 5 to the 1/3. Right? Now look what happens in this case. You don't need a calculator at all. Right? If 5 to the x is equal to basically 5 to the 1/3, these are the same. Right? So what is x then? It has to be 1/3. Right. Now here, just to verify, if you didn't know, you could either go through alpha and then window, and you see that choice number 5 is log base. You can do 5 now. Or if the software is not updated, hit math. Go down the list. You see log base function here. And it intuitively has a void for the base and a void for the argument. So you could just type 5, and then you could go for cube root. Now if you want to use cube root, there's no immediate function. You have to go through math again. Unless you want to use rational notation. This is a choice. If you have something other than cube root, you have to say a 4th root, you could use this function here, 5. I'm going to go with 4. 4. And you see that it is cube root. 5. Scoot on out of there, you have that. I could have used 1/3 at this point as well, but let's just pretend I didn't. And you hit enter. It gives you the decimal notation of what 1/3 is, right? If you like, you can convert this even still. Math, scroll over it, well, it says fraction is the first choice, and it'll give you 1/3. That is assuming that the software is up to date. If your software is not up to date, and you can kind of tell if you end up having to use a change of base formula, the software is free, right? You just gotta make sure that you have the cable of some sort. My calculator has 2 ports here. I have a USB cable and something else. This is for an instrument that you would connect here. If you at least have a USB, you could connect to a laptop or a desktop computer. Go to the Texas Instrument website and they will update the software. You may have to, sort of search around their website for it, but it's not impossible. In my case, I got this calculator in 2005, I think it was, and I hadn't used it for a while. So when I started teaching in high school was in 2009. So at that point, I had to update the software, and it took like an hour or 2 or whatever, but it's been good ever since. Okay. Anyhow, that's 3 hours in now. I think we're going to stop now. Let me leave it at that. Okay. For homework, as I said, we covered 4 sections. Beyond being aware of what the features of a transformation model would control, and you're already familiar with that, I'm not giving you homework for section 6.2 and 6.4, right? Right. Right. For homework, right, you want to do section 6.1 practice, all right, and section 6.3 practice. Okay. This is exponentials. This is logs. Okay. And today is Tuesday. It'll be due Tuesday next week. Okay. I know if you look at the calendar, there's a test coming. All right, I'll point at it now. All right. Here we are, Tuesday the 2nd. All right. I have the test written already. I'm probably going to mail it to you, but I'll tell you specifically what's going on with that, just like last time. All right, on Thursday. All right. All right, and then we'll finish basically the material. All right. This stuff is getting acquainted with exponential and logarithmic functions. This is using those to solve equations, right? And also some applications. Okay? All right.
that's it. Thank you guys for sticking with me. If you haven't yet, vote, please. It's Tuesday. All right, take care and be careful.